Okay, so today I'm going to talk about the traction vector. So what is traction vector? It is a force per area on a plane whose norm is n1, n2, and n3, and the norm is 1. And as we can see from this 3D body, on this face, there are three stress on this face. And as we can see, there are sigma xx, sigma xy, sigma xz, and the first letter denotes the norm of the face along the x-axis here, and the second letter denotes the direction of the force, which is on this one is the x, this one is y, and this one is z. So, and also we have the norm of this force is 1, 0, 0. So the traction is just the stress, tensor stress, dot the norm vector. Therefore, T is the sigma dot n, and T and n are both the column vectors, and sigma is the tensor stress. So we can write it in the general form as Ti is equal to sigma ij dot nj, and the summation of j is from 1 to 3. So if we have the traction vector on a plane, except for the normal stress, we also have the shear stress. So for example, on this plane, we have the traction here, and the norm force is sigma n, which is norm of this plane, and this one is just the shear stress. So the traction vector is actually just the sum of norm stress and the shear stress. So how to calculate the normal stress? So this is actually just the projection of T on n. So we can just apply the dot product T dot n over the norm of n dot norm of n dot n. And the shear stress is just the traction vector minus the norm stress. So let's do an example. So I have the stress tensor here. So for part A, we're going to determine the traction vector on plane, which is normal to the vector n, which is minus I minus j plus 2k. And for part B, we're going to determine the normal stress and the shear stress on the plane of part A. So of this vector, we have minus 1, and minus 2k and 2k here. So we normalize it, and we can get minus 1 over square root of 6, minus 1 over square root of 6, and 2 over square root of 6. So as we talked before, the traction vector is just the stress dot n. So traction here is the stress tensor we obtained from above, dot the n, which is the normalized of the vector. So we have the traction vector here. And B, we're going to calculate the normal stress and the shear stress. So for the normal stress, we have the T traction here and the N here. So we use T dot N, and that is the magnitude of the normal stress. If we want to find the direction of the normal stress, we just dot the N here, so we can have the direction of the normal stress. And for the shear stress, as we talked before, it is the traction vector minus the normal stress. So shear stress is the traction vector we have here, and the normal vector here. So we have the direction of the shear stress. And finally, we're going to find the magnitude of the shear stress. So we just normalize it. So the final answer is 24.15.